Let's continue with the second part of those talk.
Thank you, Noam. So thank you for continuing with us. So now that we know what are unit games and all of this fun stuff, we can forget all about it, focus on 2-to-1 games and start doing actually some Boolean analysis, well, in a few minutes. So let's recall this conventional wisdom. So we want to find a code with the following properties, ready to be complete. To be sound. So right now we're talking about 2-to-1 games. So we want the code to have a testers. Okay, sorry, we want a code and a tester. So we want the tester to make something which is a 2-to-1 check. So we want do query, 2-to-1 test, 2-to-2 test. Let's say that. And finally, we have this condition about the blow up. We want the code to be not too small. Capital M. We want C to be at least polynomial in the dimension. This is exactly the convention. Sorry? You want to be large. So this is the conventional wisdom. This is exactly as we had in the slide. And right now I'm going to try to convince you that if you're willing to let one of these slide, let's say that you're willing to give up this condition 4, then actually coming up with a code is not that hard. And it's been known for, I don't know, 10 years or more than that. So I'm going to describe to you a code and a test. I'm not going to prove it. That satisfies everything except for 4. And this is what is called the long code. So in this setting, the alphabet sigma is some large finite field FQ. Think of Q as constant, but as a large constant, a million or something. And your code C is going to be only dictators. So code C consists of all of the strings, which are evaluations of functions on FQ to the M. The function F is a dictator. Yeah. Let's take this precise thing. So this is what is often referred to as long code. So I claim that this test is okay. Now I need to tell you what the tester is. This is what is called noise tester. For that, let's say that we have some small parameter epsilon. Now the tester proceeds as follows. Example, a point X uniformly at random from FQ to the N. Example Y, which is 1 minus epsilon correlate with X. I'm using norm notation. By that I mean that I keep each coordinate as is with probability 1 minus epsilon, and otherwise I resample it from FQ uniformly and independently. So I collected these 2 points, and now I'm going to evaluate my function f on 2 of them and ask whether the value changed or not. This is the tester. This is the noise tester. It's as simple as it gets. Now let's think about it. If my function f is indeed from the long code, if f of x is this xi, then I claim that the tester passes with probability at least 1 minus epsilon. Right? This is because the probability that I kept coordinate I in place is 1 minus epsilon, in which case the test accepts. So this is simple. The test is complete. Well, it has complete as 1 minus epsilon. Soundness, well, soundness is more tricky, but it's not too difficult. So you can prove. So you want to do folding if you're actually doing PCP, but if you just want to do a tester, then it's good enough. Because the issue with folding is that you just want to avoid constant functions. But let's let it slide. Let's say that the function is balanced. So okay, because your value is annoying, I'm going to need to write a precise claim. So suppose I have some function f such that for each a in fq, the probability of f is equal to a 1 over q. I'm going to say that this is balanced. Okay, well, thank you. I'm just joking. Yeah. So suppose we have such function, then if this function passes the test with noticeable probability, you should think of delta as something small, but much larger than 1 over q, like, I don't know, 1 over q to the 0.1 or something. Then the only way that this can happen is if f resembles a dictator in some sense. And there exists a variable whose influence is loud. Okay. So this is what, so we said correlation, so it's not really correlation, but this is good enough for applications. So the long code seems good. It is complete, it is sound. It is 2 query, right? We made 2 queries, and it's unique. It's even a quality, like it doesn't get any simpler than that. The only thing that fails is 4. So if you look at the length of a word, it is q to the n. And the number of code words that you have is little n, which is this is logarithm. It's not good enough, right? We want polynomial in the length, and this is logarithmic. So this is the only place where the long code fails. It's property 4, but it really kills everything. We don't know how to use the long code to prove UDC or anything remotely close to it. What? Well, we're going to go into that realm. So, okay, so we see that it's easy to find a code that satisfies 1, 2, and 3, but we want 4. So long code is something that is very sparse. So let's go on the other end and look at a code which is much less sparser and achieves 4, but then we're going to lose 2 and 3 together. So this is the Hadamard code. So what is the Hadamard code? Well, now we are going to look at the truth tables. Functions from f2 to the n to f2, and the functions are going to be the characters or the linear functions. So this is the Hadamard code. And actually, in the first hour, we already saw a local tester for the Hadamard code. Local tester. Remind us of the tester. So you pick X and Y, formally, then you check that f of X plus f of Y is equal to f of X plus Y. So this test is complete. We already saw that. It has satisfied some notion of soundness, which is not bad. You can observe that 4 holds. So this is just a computation, but this tester makes 3 queries and not 2, which is not good. So we don't know how to use it for 2-to-1 or for unique games. And in fact, you can easily see that this code is not going to have any 2-query tester, because for any 2 X and Y that are different, if you choose a random linear function, the values of f of X and f of Y are going to be independent bits. So there is not going to be any check that you can perform on them to distinguish something linear and something which is not linear. So you really need to have 3 queries. So now we have 2 solutions. Each one of them fails miserably for different reasons. And you see that there is this tension between, having enough code words versus having a test which is, strong enough to be unique. I'm not sure, Max, how low can you go on this board before people don't see anything?
When people start looking at
Now we need to look at the board, at you and at the screen. Anyway, so now we reach what is going to be eventually the solution, which is the Grassmann code. So to arrive naturally at the Grassmann code, you can basically start with the Hadamard code and try to force it to have a 2-query tester. So if you look at the Hadamard code, what you have is you have a linear function and you spell out the values of this function on all of the points of the space. But you might as well also specify the restrictions of f to subspaces and stuff like that, which give you more information. So because it's more information, maybe you can do smarter tests. And this is precisely what the Grassmann code is. So each subset. We have a code word. So you can think of this code word as we're going to denote it by capital F sub S. It's going to map what I'm going to denote by grass of NL, F2 to the L. So this is my notation for subspaces of dimension L of F2 to the N. So to each subspace, it's going to assign some linear function on it. And I'm going to identify linear functions with some vector that specifies it. So I'm going to think of the output as some vector in F2 to the N. So how does this encoding go? Well, it goes in the most natural way. First of all, we look at S. We look at the corresponding Hadamard code word. First have little fs. That's the linear function corresponding to S. And then this capital Fs is just going to be the restriction of Fs to a subspace. Cool. So this is the Grassmann code, and this is going to be the main hero for if you want to prove hardness for 2-to-1 games. So this is the code, but now we need to tell you what the tester is. So tester. So once again, we have some assignment that gives to each subspace a linear function. And we want to test whether this assignment is a Grassmann code word, namely if it arrives from some global linear function, or if it's far from each one of these. Yes.
So do you also have some embedding of these subspaces? Like you're identifying them with F2 to the L, right?
So I identify a linear function on L with F2 to the L. So you can think of like some fixed identification.
Yeah.
It's not really, it doesn't really matter. Just that I can write something here which is coherent. But yeah. Any more questions? So we have this labeling that to each subspace gives some linear function, and we want to test whether it comes from one global linear function. And we want to do it using a 2-to-1 or rather a 2-to-2 test. And really, when you think about it for 5 minutes, there is really only one thing you can do. What you do is sample 2 subspaces that intersect in a very large dimension. So each one of them has dimension L, and I want them to intersect on the largest possible dimension, namely L-1. Then I'm going to read the values that F assigns to both of these subspaces. And then I'm going to check that it is consistent on the intersection of the subspaces. So this is the tester. Now we're going to start analyzing its properties. So one thing is clear, the tester is complete. If I run it on an actual code word from the Grassmann code, it's going to accept with probability 1. Secondly, it is clear that, well, you can just calculate the length of the code word here. So if you calculate the number of subspaces of dimension L is roughly 2 to the L times n. And the number of words that I have is 2 to the n. So they are polynomially related as long as L is constant, and it is going to be constant. So we have the property for going for us. The blow is not too much. So now we only need 2 more properties. we need the tester to actually be a two-query tester. Well, it is two-query tester. And we need it to be 2 to 1, or rather 2 to 2. And it is, because let's say that I tell you what is the value of FL. Then for the tester to pass, you must assign FL prime to be this specific function on one dimension lower. And then there is only going to be one extension to L prime. So, right, so if I tell you what is the assignment to L, then I've told you what is the assignment to this part of L prime, and you only have one more dimension in L prime, which can either be 0 or 1. So there are two options. So we only need to prove soundness, and then we're done with this lecture. But this is where, life become complicated. What about the soundness? So this is really where all of the fun starts. So when we started thinking about these things, we thought that, well, the test is going to surely be sound, like all tests that are reasonable are sound, and therefore we are going to finish. And then you formulate a statement and you try to prove it. This is going to be false. I'm going to write something false just, for storytelling. So what would you expect? You would expect that if you have an assignment F that passes this test with noticeable probability, then it must be because it's correlated with something global. Then you would expect there to be linear function such that capital F agrees with little f on a lot of subspaces. So this is the most hopeful statement you can come up with, and you can try to prove it, but you'll not succeed because it's just false. And if you remember, in the first hour, we said that for the test to be sound, it must be the case that the underlying graph is a small cell expander. So actually, right now, we're going to construct the test graph. This is going to be called the Grassmann graph, and we're going to show that it's not a small cell expander. In this case, it's fairly straightforward to see what the graph is because we specified the test very clearly here. So the vertices of the graph, all of the L-dimensional subspaces. The edges, well, there is an edge between L and L prime if they intersect in dimension L minus 1. So this is the test graph that corresponds to this tester. So in order to show you that this statement is false, it suffices for me to show that this graph is not a small cell expander. So I'm actually going to show you two examples. One of them is going to be very similar to all of this dictatorship stuff that we've seen, and we've also seen in Max's talk. And for historical reasons, I'm going to call this zoom-ins. This is just one set in the graph that is small and doesn't expand very well. And it proceeds as follows. Some vector f to the n, which is not the zero vector, and consider all of the subspaces that contain x. Let's look at the size of this set, as well as the edge expansion of it. So if you look at the measure of Zx, you'll see that it is roughly equal to 2 to the L minus n, which is small. So I should mention here that whenever we think about the Grassmann graph, we're going to think of L as some large constant, and L is much larger than L. So this measure is just little of 1 for us. But on the other end, we can consider the edge expansion of Zx. Let's think about it. If we have L inside Zx, it means that the point x is somewhere in there. And now we take a step in the graph, namely we move to L prime, which intersects L in dimension 1 less. So it's going to be some L prime like that. So because they intersect in dimension L minus 1, they share half of the vectors, and the probability that x is one of the shared ones is just half. So when you do all of this computation, you can prove that the edge expansion is roughly half, like half maybe plus little of 1. And this immediately shows you that this graph is not a small cell expander. So I should say that these type of examples exist in essentially, I think, all of the domains that we discussed so far in this workshop. Really dictatorship, because everything depends on whether x is inside L or not. So we've seen this type of stuff in Max's talk, also in Noam's talk, when he talked about Sn and where a specific element is mapped to. But the situation in the Grassmann graph is a bit more complicated than that. So actually there is yet another type of non-expanding sets which we have to think about. And again, for historical reasons, I'm going to refer to it as zoom outs. Maybe I should switch the board. So what am I doing?
Just a quick question. The plus little of 1 is because L prime might be chosen the same as L?
No, it's because they always share the zero vector. So the zero vector doesn't count. So it's like 2 to minus F one direction. I don't know which. So what are the methods? So one way to think about it is you have L, you can take the dual of L, and then insist that the dual contains some vector. This is one way to think about it. Another way is, as I'm going to state, as hyperplanes. So take a hyperplane. And consider the set ZW, which is all of the subspaces that are inside W. Then again, you can compute the measure of ZW. So, generating a subspace of dimension L is kind of like generating L independent vectors. W contains half of the vectors, so probability each one of them is inside W is half. So you roughly get 2 to the minus L. Very small. And once again, when you look at the edge expansion, you can do similar calculations to before and observe that the edge expansion is again roughly half.
Means a subspace n-1.
Yeah.
Earlier you said that you want L to be a constant because you need this blow-up condition. So now,
So everything is constant, but relative to what? So I want L to be large, but when you think of L, you project it to N, it's like small. Yeah. So both of them are large, but N is like, so you should think of L as being very large, and N is like 2 to the 2 to the 2 to L or something. Yeah, and you need to take L to be sufficiently large with respect to epsilon. So there are many quantifiers here that I'm swiping under the run. So we started with this optimistic statement. From last hour, we know that if we want this statement to be true, the graph has to be smaller than standard. Then we showed it is not smaller than standard. Therefore, the standard is false. This is a very convoluted way of saying the statement is false. So let's collect together everything that we saw, and just try to spell out an example that refutes the statement. I'm going to do just combine the picture that we saw with these sets. So here is what we do. We know that small sets that don't expand exist. So just pick a bunch of them to cover a lot of vertices. ZX1. I don't know. Let's do a bunch of sets. If you remember from the slides, now for each one of these parts, we are going to choose a completely different linear function. And this is going to be our assignment. This is the counterexample that refutes the statement. And at this point, you say, okay, the code, the test that we have is not sound. It's not ever going to be sound. But maybe we can relax the notion of soundness to be, this. Maybe this is the best that we can expect. So there are two questions. Is this the only type? Counterexample. Statement. That would be an interesting question on its own, but it wouldn't be relevant to PCB whatsoever as long as we hold this conventional wisdom. So the second question is, so I'm going to shortly formulate a statement which captures A, but the second question is, does this type of soundness suffice for us in order to construct a PCP? And the short version is that the answer is yes to both of them. And the longer answer is that I'm not really going to discuss this point anymore. Maybe tomorrow we'll see how it goes. Because to do that, you have to dwell into this, PCP constructions and start with label cover, do power repetition. Nobody has time for that now. Instead, we're going to think about this question. We're going to try to formulate precise statement that captures it, and then say how this relates to this notion of global hyperconductivity, and in fact, kind of motivates it. So now I want to formulate a statement which fixes this one and takes this type of examples into account. And notice this recipe is general, like whatever small sets that don't expand you give me, I can give you an example. We saw two types of examples, this zoom ins and zoom outs, but you can actually combine them to get new examples. For example, you can take it to intersection of those two zoom ins, you can show that it is still small and still has expansion which is bounded away from one. In fact, you can take intersections of constantly many of these, constantly many of these. You can go wild with it, it still produces a new example. And this is all that we know to do. And if you want to formulate a statement like that, you have to take by faith, this is the only thing that exists. Now, this is no longer a statement, it is true. So for every epsilon greater than 0, there is some R in delta such that if F is an assignment to the subspaces of linear functions, it passes the Grassmann test with probability epsilon, then, so first of all, I want to say that there exists some small set that doesn't expand. And secondly, I want to say that from that small set, I have some actual linear function which is global. So if I have something like that, then there exists subspace X and subspace W, both inside F2 to the N. The dimension of X is not too large. The codimension of W is not too large. I have these two subspaces X and W, and I have a linear function such that if I look at the small set that doesn't expand, that corresponds to X and W, which is all of the subspaces that contain X and that contain W, then on that set, I do have a global structure. Good question. You need L to be sufficiently large with respect to epsilon. Yeah, but you should think of R as, so R is actually going to be log 1 over epsilon. Should we care about? No, but I want it for every L loud enough. So we're trying to play parameters. Yeah. Anyway, so this is the statement, and this is true. And in some sense, this is the best thing you can hope for in light of this picture. Yeah, good. Yeah. Must satisfy my promises. Remark. So this theorem only gives you one small set, but in fact, you can see that once you have one small set, you can find many. You can iterate this statement in a sense. So let's say that I invoke this statement, I find my small set, then I look at it and I erase it. Formally, what you can do is just randomize the assignment there. Then you can find a new set using the theorem again, a new set. And this way, you're going to find many sets that cover a lot of the space. So remark by iterating statement and find many. What WI that cover at least omega epsilon subspaces. This is actually important. You need it if you want to use the theorem to analyze anything. So this is the theorem that we're after, but this theorem is, fairly complicated for multiple reasons. First of all, the main object in this theorem is an assignment to the vertices by some vectors. This is something fairly hard. We want something simpler. Like maybe we can reduce this term to Boolean functions over the vertices. That would be nicer. It would be simpler. And besides that, there are many things floating around here. This is unavoidable in a sense. So the next question that we are going to ask ourselves is there some simpler statement about Boolean functions which is equivalent to it? And it turns out that there is one. And for that, I'm going to define pseudo-randomness of sets, which is along the lines that Max defined earlier. Definition. So we say set of vertices is R epsilon to the random if I want to say, well, S, you should think about it as a small set. And what I want to say is that the density of S, the relative density in any small set that doesn't expand is still very small. So if for every X W subspaces such that the dimension of X, the codimension of W, is most R, it holds that the density of S in that set is most epsilon. So for now, we call this set pseudo-random, but actually nowadays we more often call them global, because if you have some density, some x and w where the density is large, this is some local structure of your set. And if you don't, then it means that your set is global. And what the expansion theorem is going to say, or global. What the expansion theorem is going to say is that the only sets in the Grassmann graph that have expansion which is poor must be local. Or equivalently, for every epsilon greater than 0, there is some r delta such that if S is R delta pseudo-random, then the edge expansion of S is 1. Okay. So now we have two statements, two theorems that seem to really try to get at the same type of structure in the Grassmann graph. They both try to say something about the structure of non-expanding sets. This theorem is much cleaner, it's only 3 lines. This one is many more. So this is something that kind of more natural to try to prove. And indeed, once you start this statement, at least you can try to do some Fourier analysis to get something. Well, this statement seems unapproachable by Fourier analysis. Like, what are you going to expand to Fourier basis? And indeed, you can start looking at the connection between these two statements, and it's an exercise which is not too difficult to show that this theorem implies the expansion theorem. This is fairly easy, but the actual thing that we want is, the plan is, let's prove this and show that this actually implies the harder theorem. And this is true, and this is due to Barak, Kohtari, and Stower. So, so I have 10 minutes, which is enough to give a rough sketch of this argument. But basically what I'm going to tell you is that this theorem tells you that if you want to analyze the Grassmann test, then it's enough to analyze expansion of the Grassmann graph. And this is something that you do using Fourier analysis. Maybe we'll see later, maybe we'll discuss some of it tomorrow, maybe not. We'll see. For the rest of the time, unless there are any questions, I'm just going to sketch this argument just because it's very cute.
Sorry, what was the conclusion of expansion theorem? Because we can't see it from here.
Yeah.
Just right at the top. So just the last line.
That's that line. Yeah. The conclusion is that the edge expansion of S. Now we just move to the side here. Sure.
You walk there, we can see.
So this is all somewhat visible? Okay. Anyway, edge expansion is plus 1. Any more questions?
there any way to sort of identify vertices, do some group action, etc., to kind of get some graph, which is an honest SSE from this, which might also suffice? It's a sort of e-post question.
I don't know. I just but not. Definitely good. I don't know. Somehow, at least for this stuff, the only group action that I can think of collapses the whole graph.
Constraining and HDX, and maybe that's it.
I think none of them is going to be smarter expander.
And they just want to expand. No.
Yeah. I don't think that you can do some black magic to get into a smarter expander. Like, yeah.
This conjecture about short.
Yeah, but short code. So here, the size of the number of code is called a number of code is polynomial in the length. So the short code is not quite polynomial.
I mean,
Quasi polynomial.
the conjecture is that you can get into it.
There's a little of wonder which is going to mess up your life. But, yeah. Okay. So 7 minutes. 7 minutes is pushing it for the proof or the define anyway. So we are assuming the expansion theorem and we want to prove this statement. So we have an assignment capital F and want to define some set of vertices using it. So how do we do that? So we fix an assignment. Now we're going to do something very odd. We're going to choose a linear function randomly. We choose a random linear function, and we're going to look at the subspaces which the assignment capital F agrees with this random linear thing that we sampled. Okay, this is really odd, but this is what we're going to do. Now we have a random set of vertices, and we're going to try to compute the expected density of it and the expected edge expansion and hope for the best. What is the expected density? Well, if you play around with this, you can use linearity of expectation, and then essentially the question boils down to, for a fixed L, what is the probability that when I choose this function little f, it agrees with the assignment capital F on L? And the answer is just 2 to the minus L. So the expected density is 2 to the minus L, which is very small. That's fine. This is what we get. So now, what is the edge expansion? Well, I'm going to try to compute or estimate the number of edges that stay inside. Let's see. So I'm going to write that this is at least. So I'm going to range over all of the edges on which the test passes. And I'm going to ask, what is the probability that both endpoints lie inside SF? So let's see. So the probability that L is inside SF is 2 to the minus L. We already computed that. But now condition on it, what is the probability that prime is inside? Well, we already know that capital F of L prime and little f agree on a subspace of L prime of dimension L minus 1. This is just L intersection L prime. And there is only one more dimension. Probability that you agree on that is half. So this is 2 to the minus L times half. When you calculate it, you see that the number of edges, the expected number of edges that stay inside SF is at least 2 to the minus L plus 1 times the number of edges on which the test passes, which by assumption is at least f to the fraction of total number of edges. Now we just look at the expected number of edges that stay inside, divided by expected size of SF. Number of edges that stay inside, divided by d, the degree, times expected size. I just plug in all of these calculations, and I see that this ratio is at least epsilon over 2. So from this, you can conclude there are 2 ways to do it. One of them is the wrong way and one of them is the right way, but I'm not going to say too much about it. You can conclude that there exists an F where this ratio is achieved. And when you do 1 minus that, you get here the edge expansion. So you get there exists an F where the edge expansion of SF is most 1 minus epsilon over 2. Okay, so we did all of this random set argument, and finally we indeed managed to get a small set or something that looks small, which has expansion by the way from 1. At this point, you can apply the expansion theorem and get that SF is dense inside some non-expanding set. And if you think about it for a moment, you realize that it means that inside that non-expanding set, our capital F and our little f agree on many of the vertices. And this concludes the proof of the theorem. So yeah, so this is a very cute argument by Barak, Kotari, and Storer. And it shows you that if you want to study this, completely looking theorem, it's enough to look at the expansion theorem. So this is all I wanted to say for today. And tomorrow, we'll see what to do. But maybe I'm going to talk about the expansion theorem. Maybe I'm going to talk about some other domains in which you can hope to get, on which you can get something like that, and other applications. So that's it for today. Thank you.
Let's think though for. Are there any questions for Doro?
Yeah.
So if you relax requiring exact agreement in this theorem to approximate agreement, can you still use it for PCP? Can you hope to get it sort of relaxed?
Here?
Yeah,
What do you mean by approximate?
like you agree on most of the function, it's like something like people look on the complete complex.
Yeah, so on a complete complex, this makes sense.
Right.
But here you're dealing with narrow correcting code. So either you completely agree or you agree on half of the things. So this is a very good question. Yeah, it's an history question. Yeah.
So this final argument you showed, is there a more abstract statement here that if you're an SSE, then agreement tester has some soundness? Yeah, this last thing.
So there is exactly one point in the argument where we use something extra about the test, which is not generic, which is this half. So, if you have a D2D test, then all of this argument works out. But if the test is not D2D, then it will break. It still seems like, generally speaking, there should be a relation between expansion theorems and agreement theorems, but I'm not familiar with a very generic form of it. So this Grassmann graph is a regular graph. So when I say degree, I'm just mean the degree of a vertex in a graph.
Is there like a, for the Johnson graph, is there an analogous like code for it? For the Grassmann graph?
Yeah. So this is actually what Max was asking. So this direct product test and stuff like that. So this has applications in PCP, but not for PT1. Yeah, but yeah, much of what I said can be extended to there. Actually, it's a little simpler, but historically speaking, this came first. And, yeah.
So if you want to prove 1 to 1, then what do you want to change?
Doing F1. These are fun. So the 2 here comes because we're working with F2. So if I give a linear function over the dimension m minus 1, there is 2 extensions.
Right.
To dimension 1 more.
So let's say you want to prove UGC, and say what kind of extra.
So if we want to do them with computation, so this maybe you need to take like a tensor or something.
Yeah, so there are several ideas all in the fail, as far as I know. I don't know which fails more to tell you. Yeah. It's a good question. I don't know the answer.
So you could take sets and computations, and then this thing of fails is the so what's the test? Linear functions, just like computations instead of subspaces, take sets.
No, but the Johnson is not going to have
Yeah,
it's
it's not
basically
going
going
to
to
have expansion.
yeah, okay. The sum is also going to be close. Anyway.
Let's thank Laura again.